Hello, we are Group 6 and we will be presenting today on our polynomial regression model. So we will be going over the models that we used for the baseline and the regular model, the data that we used, where we got it from and how we tuned it, the hyperparameters and the tuning, and the graphs of both the baseline and the polynomial regression model, and the analysis between the two.
Hello everyone, my name is Pepper and I'll be discussing the models we chose to use. So for our baseline model, we chose linear regression. We discussed this in class, so I won't go into too much detail, but essentially we draw a straight line across the data to try and minimize the difference between the predicted and actual values. Polynomial regression is an expansion of linear regression. Instead of attempting to draw a straight line to fit the data, polynomial regression uses a curve instead. So if you remember high school algebra, it's essentially these functions here, where as you can see, we have the bias here and each of the weights on each of these exponents. So linear regression is actually polynomial regression just to the first degree. As a model, polynomial regression uses the polynomial equation up to a certain degree, and it tries to find coefficients for that best fit the data. And the way it does this is using the gradient descent algorithm. And during gradient descent, the model updates the coefficient by the amount specified by the learning rate, and does this update n times, which is specified by the number of iterations. Gradient descent is basically an algorithm for reducing loss in a function. It takes in a cost function and the learning rate. The cost function essentially models how incorrect the function currently is, and the learning rate is how much the algorithm will try to change. So how gradient descent works is it takes a tangent line from the function, and this is the gradient, and it tries to minimize that gradient. So it takes the slope of this and tries to get it as close to zero as it can. So the learning rate for gradient descent can be tricky. Lower values are more precise but much slower, and higher values can run a lot faster, but they have the risk of overshooting the minimum. So things like the optimal learning rate, optimal number of iterations, these are discussed during hyperparameter tuning, which we will discuss later.
Hi, my name is Justin, and I'm going to be talking about the data we chose and why we chose it. So, originally, we were going to go with something like supply and demand with oil or something similar to network traffic, but ultimately, we decided to stick with age versus income. And there were a couple of reasons for this. So, for one, there are many data sets on age versus income on Google. We got us on Kaggle, and because age versus income is studied a lot in today's world, and that for another, in the real world, age versus income is not a linear relationship, so it has a curve, kind of like a hill, where income usually starts in the early 20s, peaks in midlife, and then declines near retirement. A linear relationship wouldn't work because a 90-year-old usually won't make more than a 40-year-old or maybe even a 20-year-old sometimes, but usually wouldn't. Um, for our data set of 50,000 or around 50,000 entries, we only picked 1,300 entries around from it. And this data set included all demographic data. It had age, income, race, social class, marital status, hours per week, and others. But we only took age, income, and hours per week. We used the age and income as the X and Y, and we basically used the hours per week to standardize the hours that people work to be 40 hours a week and adjusted the salaries according to that. We also used the z-score to filter out the outliers outside of 3 standard deviations of the mean. So working the 40 hours a week standardization and the z-score was to make our graph smaller so we could actually see that curve. And for those 1,300 entries, we made an 80-20 split for our data, where 80% of our data subset was used for training, while the remaining 20% we used for testing. So for the training data size, we had around 1,022, while for the testing data size, we had around 256.
Hello, I'm Alexi, and I'm going to be going over the hyperparameters and the tuning of our model. So there are three hyperparameters that are used in polynomial regression. Those are the degree, learning rate, and number of iterations. The degree is basically how complex the model is and the type of graph that it produces. If it's too small, it might not fit the data very accurately, but if it's too big, it may overfit the data. The learning rate is used for the gradient descent, and the greater number of iterations, the closer you can get to minimum loss for the number of iterations. We used a loop on our polynomial regression model to determine the most optimal hyperparameters for each degree based on the highest R-squared value on the testing data when used on the training regression, and we chose the best option. In this case, it was degree 4, as you guys can see, and the learning rate was 0.0125 and the iteration number of 995. For the range of inputs, we chose the degrees to be from 1 to 6, learning rate to be between 0.0005 and 0.1, and the iterations to be between 500 and 1,000. We limited this range due to the computational issues with Python. When we would reach a certain point on higher degrees, we would receive an overflow error, and this is most likely due to the size of the salaries that we were operating on, and combining that with a higher power, it was not avoidable in this instance. We also limited the iteration number from 500 to 1,000 because the higher the iteration number was for the degrees that we had above, the R-squared value did not get much larger. So increasing the iteration number in this case of our dataset was not beneficial past 1,000, but could be beneficial for other datasets.
My name is Jet, and I will be covering the graphs and analysis section. First are our linear regression graphs, and this is our baseline, by the way. Both our training and testing graphs look about the same as far as our line of best fit, and they both display the trend that as you get older, your salary slightly dips. Next are our polynomial regression graphs, and they both show the trend that when you are younger, your salary is a little bit higher, and then in the middle stages it dips a little bit, and then in your later stages in life it seems to go up a bit. And as you can see here, our testing graph looks a little bit different from our training graph because it looks a little bit more parabolic in nature. This is mostly due to the fact that our data is just too scattered, so the model struggles to find a curve to best fit the data. Now, when we compare our models quantitatively, we used R-squared and mean squared error to do so. Now, our polynomial regression performs minimally better than linear regression because polynomial regression has a slightly higher R-squared value and a slightly lower mean squared error value as opposed to our linear regression. We could have made our model a little bit more accurate if we were able to test higher degrees for our polynomial regression. However, when we tried using degrees of 5 or higher, Python kept giving us overflow values, which prohibited us from doing so. Moreover, we could have been more accurate if our data wasn't so skewed by so many outliers, because this made it difficult for our model to predict accurately. This is our works cited, which includes Kaggle, the website we got our adult income data set from. Thank you for listening and have a nice day.